So we tried solving this question using the equations of motion alone. Now what we'll do is we'll try to solve the same question, but this time using the concepts of work energy theorem. Okay. Now before we go much into work energy theorem, let me just try to explain the basic problem that all of us address while solving the questions in this chapter. Well, before we go into this, let me also say that this is gonna be a very lengthy way of solving the question, right? This would be unnecessary complex and would be a long way of solving the question. Okay, and how to do it in a faster way? We already have done that like this using equations of motion. Then why are we trying to learn this? Although this is unnecessarily complex and long, because this is what will help you in a kind of interlinking concepts and interlinking chapters in interlinking concepts in multiple chapters, bringing all these concepts together and then try to pull out one simple solution out of it. So basically that is what comes as the primary demand in the JEE advanced. This question is definitely not at the advanced level, but we are trying to understand that such an simulation is possible here. Okay, right. So what are the two possible situations that we encounter in physical systems? We can say systems which comprise either of conservative forces like gravity, or which comprises of both conservative and non-conservative forces. Non-conservative forces being like friction in the system, or any other resistive force in the system. Now, the whole workflow varies according to the presence of conservative and non-conservative forces. How? Let's have a look at that. So if we are trying to solve questions based on the concepts that we learned in work energy power, this should be your primary flowchart. You should first search, are there any conservative forces acting in the system? If there are any conservative forces acting in the system, if the answer is yes, then you'll use law of conservation of mechanical energy and apply energy conservation, which means total energy final should be equal to total energy initial, that is mechanical energy plus potential energy. Now, if the question is such that there is no conservative forces acting, or in other words, if there are non-conservative forces acting in the system, then we will be using which theorem? We'll be using work energy theorem, and then calculate work done by all forces. Okay, I hope that makes sense. So we have a system, and if the system has only conservative forces, then apply law of conservation of mechanical energy. We have system, and if we see non-conservative forces being present in the system, then we use work energy theorem, and then we calculate work done by all forces. See, this phrase is really important. Work done by all forces, not work done by one force. Work done by all the forces acting in the system. Okay, now in this condition, in the question which is given to us, what are the various forces acting on the bullet here? There can be many forces. There can be frictional force, normal force, impact force, resistive force, gravitational force, which is caused by the weight of the bullet. There can be air resistant. There can be deformating forces within the plank. So there are multiple forces which are acting in the system. Now, in this question, to be more precise, in this question, what we need to understand is most of the forces here are neglected. Most of the forces here are neglected, and the only force that we consider here is the resisting force is the only force acting in the system. Only force acting in the system. Okay, all these forces are neglected. They are negligible. The effect of them on the course of the motion of the bullet is negligible. Okay, and there is another assumption that we make. This force is the only force, which means there's only resisting force acting on the system, on the bullet, and this force is constant throughout. Okay, why is it constant? Because why is it important that it's constant? Because only then F average will be equal to the constant force. Why? We will discuss this sometime later. Okay, now what is work energy theorem now? Now work energy theorem, okay, maybe we'll just go back to this flowchart. So as we said in this question here, we have one a resistive force, and resistive forces are non-conservative in nature, which means we will be using work energy theorem in this question, right? Now what is work energy theorem? Work energy theorem states that the net work done on the body, on the object or the system, is equal to the change, not work done is not on the system, net work done on the object or on the body will be equal to change in its kinetic energy. So W by net, the net work done will be equal to kinetic energy final minus kinetic energy initial. Now what is net work? Net work is the total work done by all forces acting on the body. Okay, now in this case we consider only the resistive force that acts on the body, and since this is a resistive force, it offers resistance to the free flow of the free motion of the bullet, and therefore it does negative work. Why? Because it reduces its kinetic energy, bringing the velocity eventually to 0. Now the next question comes: can law of mechanical energy conservation be applied in this scene? No, mechanical energy conservation cannot be applied in this scene. Why? Very simple logic, because the mechanical energy is not conserved. But the question is, why is it not conserved? Why? Why is it not conserved? It is not conserved because the resistive force exerted by the target, which is the plank, is non-conservative because it converts the bullet's kinetic energy into other forms of energy, mainly heat and deformation. And therefore, initial mechanical energy is not equal to final mechanical energy. Why? Because some of the initial mechanical energy is now lost in the form of heat and other deformation, maybe sound as well. Okay, see, this much is the crux of work energy power. And in fact, the crux of the chapter, work energy power, and how to use, not work energy power, I should, the topics work and energy. And if you understand this crux, you'll be able to solve almost every question based on the topics. Okay, so now we will get into the direct solution. So we know that by work energy theorem, work done by all forces is change in kinetic energy of the bullet, which is kinetic energy final minus kinetic energy initial, and we assume that all other forces are negligible and the only force acting here is the resistive force. Okay, now every other constraint that we have used in the previous solution remains the same here, where B is the point where the velocity loss is 1/3 of the initial velocity, C is the point where the bullet is at rest, therefore velocity at B will be 2v/3 and velocity at A remains A. Now for the motion along AB, kinetic energy initial will be half mv square at A square. Kinetic energy final would be half m at B square, which is 2v/3 the whole square. Now, what is kinetic energy final minus kinetic energy initial? We know that by work energy theorem, it is work done by the resistive forces, which can be written as force into displacement. Maybe I'll just write it over here. So we can write that work done by the resistive forces can be written as force into displacement. The force is F resistive into displacement is S, which is equal to KEF minus KEI. Now, KEF is half m to v/3 the whole square minus KEI is half m into v square. I've taken out half m common from these two terms. It is given to us in the question that the initial displacement is 4 centimeter, right? This 4 centimeter over here. So we can write displacement as, we can replace this displacement as 4 into 10 to the power minus 2 is equal to half m into 2v the whole square by 3 is 4v square by 9 minus v square. 4v square by 9 minus v square is minus 5v square by 9. And therefore, F resistive is equal to mv square by 2 into 5 by 9 into 10 square by 4. 10 to the power minus 2 to the RHS will become 10 to the power plus 2, which gives us mv square into 125 by 18. Okay. So, okay, yes, so that's that. Wait, let me just confirm this. So we have 425, 25 into 5 is 125. Okay, right, 125 by 18. Now what happens to the bullet? After getting this F resistive, it penetrates further and eventually it comes to rest. So B is the point where the velocity is 2v by 3 and eventually it comes to C where the velocity is equal to 0. Now if we apply work energy theorem for this motion, for the motion along BC, F resistive into S will be equal to kinetic energy final minus kinetic energy initial. Final velocity is 0, so kinetic energy final will be equal to 0, right? Initial velocity is 2v by 3, so kinetic energy initial is half m into 2v by 3 the whole square. Now, F resistive into S is equal to 0 minus half m into 4v square by 9. We have found out in the previous section that F resistive is equal to minus mv square into 125 by 18. We'll bring that over here. So we'll replace F resistive as mv square minus mv square into 125 by 18 into S is equal to minus half m into 4v square by 9. Now, to simplify this, m by m is 1, v square by b square is 1. So all we have is S is equal to 1 by 2 into 4 by 9 into 18 by 125. Now what is S? It is given in the question that it is d into 10 to the power minus 3. So d into 10 to the power minus 3 would be equal to half into 4 by 9 into 18 by 25. I'll transpose this 10 to the power minus 3 to the RHS as well. So what we get is half into 4 by 9 into 18 by 125 into 1000. Now comes the simplification. 125 times 8 is 1000. 9 2s are 18, 2 2s are 4. So we have 2 into 2 into 8, which is 32, which overlaps with the previous answer that we got. Okay, so this is how you solve a question using work energy theorem. Now, if you have understood this concept here, if you understood the logic behind solving the question here, I would suggest you try solving the same question, this time using impulse momentum theorem. Try solving it. If you get the correct answer, get back to me. If you find any concepts which are missing in this, or that you find is difficult to solve with using impulse momentum, get back to me. We will try to solve it one more time. And again, let me just confirm this. Even if you try solving this impulse momentum theorem, this is also going to be unnecessarily complex and is going to be long and will have more arithmetic calculations. But the reason why we are trying to try to solve it that way is just to make sure that you get to connect concepts. Okay. All right. Now, moving on to the next set of questions based on bullet and block.